Okay, the next class of organic compounds that we're going to talk about are the Halogenoalkanes. As the name might suggest, these groups or this class is really just alkanes, but they have a halogen, one or more halogen atoms attached to them. So the functional group for this class is just a halogen atom. So it could be a fluorine atom, a chlorine atom, a bromine atom, or an iodine atom. It also could be more than one of those things. The compound is going to be called a halogenoalkane if it has one or if it has more. They all fall into the same class. Halogens can also show up attached to other types of compounds. So as we learn more types of compounds like alcohols or carboxylic acids, you can also have halogens attached to them, and you'd probably then call that molecule the other type of compound. Like if an alcohol has a fluorine atom attached to it, you'd probably still refer to it mainly as an alcohol and consider the fluorine just a little side attachment. It's not really going to be an issue on the IB exam, but just to point out that that is a possibility. So we know that halogens generally only form one covalent bond because they already have 7 valence electrons. And so they're always on the outside of these organic molecules. We're never going to have halogen atoms in between carbon atoms. So it makes it pretty simple to figure out how to draw them. So you've got alkanes, and then you have really 4 different kinds of halogenoalkanes. But we can just call them halogenoalkanes collectively. So if you have ethane, C2H6, the halogen atom is just going to replace one of the hydrogens, and so you get C2H5F or ClBr or I. In terms of names, unlike most of the other functional groups that we're going to learn about, the halogen gets added to the front of the name in the same way that a methyl or an ethyl would get added to the front of a name. So in a way, it's almost considered as like a branch or a side chain rather than a really important functional group. So this is called ethane, fluoroethane, chloroethane, bromoethane, and iodoethane. In terms of their IMFs, well, while alkanes only have London forces because they are just made of C and H, so they're completely nonpolar, the halogenoalkanes do have some polarity to them. Going towards fluorine, so as I've drawn them, the trend from right to left would be that we've got increasing polarity and therefore some sort of increasing dipole-dipole force. However, as we go to the right, we have the size of the atom, so F to Cl, Br to I, is increasing. And so we have an increasing amount of London forces as we go to the right. So it's a little bit hard to predict which type of halogenoalkane is going to have the higher boiling point or melting point. And so usually you're not comparing, fluoroethane to chloroethane in a problem because it would be a little bit too tricky to figure out just by a guess. You could try to make a stab at it and make a prediction why, but the IB is not going to ask you to do that. However, they would ask you to compare them, let's say, to alkanes, in which case you would predict they probably have a slightly higher boiling or melting point because they do have some dipole-dipole forces as well as the London forces, while the alkanes only have the London forces. So that's mainly what you'd have to deal with in terms of halogenoalkanes and physical properties. They are not going to be very soluble in water because while they are polar, they generally can't form hydrogen bonds with water. Therefore, they're not very water soluble. Some other naming things to consider. As these halogens can be anywhere on a chain, it's very important that we number where the halogens are. Those previous examples did not require numbers because there was only one halogen atom, and so therefore it by default is going to be on the number 1 carbon. You wouldn't call this 2-fluoroethane, you would call it 1-fluoroethane because you always give the lowest number possible, and therefore no number is needed if there's only one of these halogens on either methane or ethane. However, once we get to a 3-carbon chain, now you do have to number it because now there's more than one possible position. So in this case, we are on the number 1 carbon, not the number 3 carbon because 1 is lower than 3, so that's how we should choose to number the chain. And in this one, no matter which direction you number from, this is on the 2. So this first one we would call 1-chloropropane, and this one we would call 2-chloropropane. And again, it's the 1 dash or the 2, and then that hyphen, that dash, and then chloropropane. So the chlorine gets named as a chloro in front of the alkane name. 3 carbons, my elephant poops. So that's P, prop, so propane for 3 carbons. If there's more than one halogen, just like there could be more than one methyl group, you're going to add the additional prefix in the same way. So if it's just one, you don't add one, but if there's 2, 3, or even 4 prefixes, then you add these other ones. I'm going to fix this because it's spelled wrong. Ooh. So should do it again. There we go. All right. So di means 2, tri means 3, and 4 is tetra. So tetra, like the game Tetris, it comes from oh man, I'm a mess right now. It comes from the Greek for 4, and so that's where tetra comes from instead of quatra or quad or anything like that from English. So this first compound would be called chloromethane. The next one, dichloromethane, trichloromethane, and tetrachloromethane. You don't need to number them when it's a methane because obviously they are on the number 1 carbon. And so if you're numbering with more than one halogen, you need to make sure that you assign a number to every single one, even if they're on the same carbon atom. And always use the lowest number possible. So here, they're on different carbons. So no matter which way I number it, 1, 2, or 1, 2, I'm going to have 1, 2 dichloroethane. In this one, I could either number it 1, 1 or 2, 2, depending on how I want to number the chain. And I think 1, 1 is a better choice. So this would be called 1, 1 dichloroethane. These other ones are just to show you that it might be represented in a different way, but it doesn't mean it's actually a new compound. This compound here is exactly the same as this compound here. This is also 1, 1 dichloroethane. And so it's not actually a new isomer because it has the same name. And this is another way to draw 1, 2 dichloroethane. So just a reminder that you can draw things on the opposite sides of the chain, but it's all about which carbon atom they're actually connected to. And so this is not a new isomer either. There's only 2 different isomers of this compound. An additional idea to incorporate now that we're talking about halogenoalkanes, and you'll do this for not just halogenoalkanes, but also alcohols, and eventually a group of compounds called the amines, is that we can classify the compounds as something that we call primary, secondary, or tertiary halogenoalkanes. They have different types of structures. The halogens are in different environments, and it becomes useful when we talk about the different types of, especially reactions that these things could undergo. It's really more of an HL concern, but you do need to be able to classify any halogenoalkane as primary, secondary, or tertiary. But it's really quite easy. In something that's primary, the halogen is attached to a carbon that is only attached to one other carbon. Secondary, the halogen is attached to a carbon that is attached to 2 other carbons, and tertiary, the halogen is attached to a carbon that is attached to 3 other carbons. So if we look down at these examples, so here's the halogen, here's the carbon it's attached to. How many other carbon atoms is this carbon attached to? Only 1. It's attached to 2 hydrogens. So this first one here is primary. So I'll just draw a number 1 and a little degree symbol. That's sometimes a convention used to label primary, secondary, tertiary. In this example, so here's the bromine, here's the halogen. It's connected to a carbon, and that carbon is attached to 1, 2 other carbons, and therefore this example is secondary. So you see, a primary, the halogen sort of sticks out at the end of the chain, whereas a secondary, it sticks off the middle of a chain. This example here is sort of a tricky one. Here's the halogen, here's the carbon, and it's only attached to 1 other carbon. So this is actually another example of a primary, even though it looks like it may be more or a higher level classification than that. And then this example is an example of tertiary, where it's attached to a carbon that is attached to 1, 2, 3 other carbon atoms. And so those are the tertiary ones. Tertiary ones are the sort of most branched and protected, as opposed to primary, where the group is sticking out the furthest. So that's classification. We'll do some practice naming in class, and we'll do some practice with isomers and naming in class as well. So the last concept to cover as we go over halogenoalkanes is that halogenoalkanes can be converted into alcohols. Now, halogenoalkanes do have a number of uses, and so one of the most famous uses of halogenoalkanes are as refrigerants, so things that are gases that are very important to how refrigerators and air conditioners work, and how aerosols can work, aerosol cans. And so they have a lot of uses. They're very important because they're fairly low reactivity. They're not toxic, generally speaking, or at least some of them aren't. And they tend to be gases, so they can be compressed well, and that's what's important for the refrigerators and the air conditioners. However, they do tend to then leak out of those devices and make their way up into the ozone layer, which is what causes the destruction of the ozone layer and the ozone hole. So we've talked about the ozone layer and ozone destruction before. And so those molecules, the CFCs, the chlorofluorocarbons, are those compounds, the ones that are affecting the ozone layer. But for the IB exam, all you need to know is that halogenoalkanes can be used to produce alcohols. And alcohols are organic compounds that contain an OH group. So really for the IB exam, all you need to know about halogenoalkanes is they are a useful sort of step along the way towards making alcohols and then making other types of organic compounds. So the overall equation for this reaction, it's a nucleophilic substitution reaction, is just that Rx standing in for the halogenoalkane, where R represents some carbon chain of any length, and X represents our halogen, and the OH minus is a hydroxide ion, which comes from some sort of a base, some sort of a strong base or alkali solution like sodium hydroxide or potassium hydroxide. It's called a substitution reaction because, as you can see, the OH takes the place of the halogen in the molecule. And so the X gets kicked off, and now it has the minus charge. And now the OH group is attached to the R. So this is the alcohol group, which we'll learn about next. And this is just a halogen ion, like an F minus or a Cl minus or a Br minus. So this reaction takes place in aqueous solution. You don't need to know any special conditions or catalysts for it. It'll just take place. And the reason why it's called a nucleophilic substitution reaction, as opposed to the other kind of substitutions that you'll have to know, like free radical or electrophilic substitution, is that the thing that substitutes onto the halogenoalkane is a nucleophile. So the OH minus, the hydroxide ion in this reaction, is the thing that we would call the nucleophile. A nucleophile, if you break down that word, is something that likes a nucleus. And why something might like a nucleus is because it's what we could call electron rich. So the nucleophile has to have at least one lone pair of electrons, one non-bonding electron pair, and it often carries a negative charge. So there are other nucleophiles that are possible. The only one you need to know about is a hydroxide ion. And so since the bond between the carbon and the chlorine or the carbon and any halogen is going to be a little bit polar, with the carbon atom having a slight positive charge, a nucleophile like hydroxide is going to be attracted to that carbon atom. And so the negative charge and the electron pairs on the oxygen will be attracted to the carbon, and a bond will form with the carbon, and that will cause the chlorine to leave and basically take these two electrons with it. So the OH group attaches on, and the Cl leaves as an ion. So that's more of like the mechanism of the reaction. And in SL, you actually don't need to know anything about the mechanism. So you should know what a nucleophile is. You should know what this reaction is called, a nucleophilic substitution. And you should essentially know that you can replace an OH for a halogen on any of the halogenoalkanes that we've discussed so far. That's the second organic reaction that you need to be aware of.